Good morning. Hello. I hope everyone had a good time at the banquet last night. We're going to get started with our final session of PacificVis 2025. My name is Matthew Bremer, and I am an assistant professor at the University of Waterloo in Canada. I'll be chairing this session, which is called Taxonomy, Generative AI, and Creative Visualization Tools. Our first talk today will be delivered remotely. It's a TVCG track paper. It'll be presented by Yu Zhang from the University of Oxford. It is called Viz Taxa, Developing a Taxonomy of Historical Visualizations. Yu, are you there?
Yeah, I'm here.
All right, thank you.
Okay, thank you for coming to this talk, and I'll be presenting our work titled Viz Taxa, Developing a Taxonomy of Historical Visualizations, and this work is to study the taxonomy of historical viz created before the computer era. As we know, visualization has a long history, and we have seen old visualizations in introductory visualization courses, such as Jon Snow's color map, Maynard's map of Napoleon's Russian campaign, Playfield's chart of economic statistics, and Priestley's chart of history. And these historical visualizations show us where our field came from and offer creative alternatives to contemporary design norms. And in this work, we are interested in investigating what visual designs have been used in historical viz. And to answer this question requires a data-driven approach that examines a corpus of historical viz and categorizes the visual designs used. And in our previous work, Old Viz Online, we have curated a dataset of 13,000 images of historical viz published before 1950, as shown in the right image collage. And such a collection provides us with the opportunity to apply the data-driven approach. How to gain an overview of the historical viz collection and understand what designs have been used, we will resort to taxonomy as a tool for answering this question. Taxonomy has long been used in the viz community for organizing the design space, and famous examples include Schneiderman's task by data type taxonomy that categorized InfoViz by data types such as temporal and multidimensional, as well as by tasks such as overview and zoom. And despite the wide use of taxonomies in the viz community, taxonomies for historical visualizations are underexplored. And additionally, we observed that the method for taxonomy development is usually not the focus of the related work and are thus often obscure. And therefore, we also aim to contribute a method and tools to operationalize taxonomy development. And in the following, I will first introduce the protocol and system we developed for taxonomy development from image corpus. And then I will describe the resulting taxonomy for historical viz that we developed with the protocol and system, and as well as an analysis of the resulting taxonomy. To ensure we are on the same page, let me first clarify what we mean by saying developing an image taxonomy. To develop an image taxonomy is to accomplish two tasks. The first is to construct a hierarchy of categories and assigning, and the second is to assign the images in the corpus to the categories. And from the data structure perspective, the first task is to build a tree where each node is associated with a name that corresponds to a taxa in the taxonomy. And the second task is an image labeling task that requires assigning each image to one or multiple leaf nodes of the tree. And additionally, we note that our work is focused on categorization by image visual similarity. We developed a 4-step protocol to operationalize the process for multiple coders to develop a taxonomy empirically using a corpus of images. And we also built a system named Viz Taxa to support this protocol. And the 4 steps are as follows. At the beginning, a batch of images is sampled from the corpus. And for the first step, each coder individually edits a hierarchy of taxa and assigns the images to the taxa. And the editing is conducted with Viz Taxa's taxonomy labeling interface, where the coder can edit the taxonomy tree and assign taxa to images. The interface integrates some machine assistance, such as using clip embeddings and k-means to cluster the images and suggest splits when dividing a taxon. And for the second step, all coders collectively discuss their disagreements on the taxonomy tree, naming of taxa, and definition of the taxa. The Viz Taxa taxonomy comparison interface is used for this tree comparison task, where the coder's taxonomy trees are juxtaposed and a merged taxonomy tree highlights the discrepancies. And for the third step, each coder individually modifies the taxonomy tree and the images labels based on the discussion in step 2, and the modification is conducted with the taxonomy labeling interface. And for the fourth step, all coders collectively go through each image whose labels differ among the coders. And for each conflicting label, the coders justify their choices, which may involve discussing the definition of the taxa and the understanding of the image and how the two align. The taxonomy comparison interface is used for presenting the label conflicts, and the coders may edit their taxonomy with the labeling interface when necessary. After a batch of images is coded, the 4 steps are repeated for the next batch, and throughout the process, the coders keep record of the edge cases they encountered and the discussion log. Following the protocol and using the VIS-TAXA system, 3 of the authors coded a corpus of 400 images randomly sampled from old VIS Online and developed this taxonomy. And the taxonomy includes 51 taxa, among which 45 are leaf-level taxa. And the middle shows the taxonomy, and the right shows the example image from the leaf-level taxa. We can see that these taxa include some familiar designs, such as various types of bar charts, and also includes some less commonly used designs, such as windrows that visualize the distribution of wind directions with small multiples. Now we want to scale the taxonomy labels from 400 images to 30,000 images in old VIS Online dataset. To do so, we use a similarity-based matching to assign each of the 30,000 images the labels of its most similar image among the 400 human-coded images. The image similarity is quantified by the cosine similarity of the image clip embedding. We conduct a leave-one-out cross-validation with the 400 human-coded images to evaluate the performance of the prediction, and the resulting J-COD score of the prediction is 0.619, suggesting the prediction is not perfect, but sufficient for us to get a coarse overview of the distribution of designs among historical visualizations. Scaling the taxonomy to a large dataset allows us to comment on the distribution, and we are ready to visit the question of what designs have been used in historical VIS and whether the historically popular ones differ from the contemporary popular designs. Battle et al. Have analyzed the distribution of chart types in the gallery of visualization libraries, and they concluded that the most frequent types of visualizations on the web are bar charts, line charts, scatter charts, and geographic maps. We quantify frequent as occurring in more than 5% of the images, and find that the most frequent types of historical visualizations are mostly consistent with contemporary ones. Map, bar chart, and line chart are among the most frequent types. But interestingly, we find that while scatter plots are commonly used nowadays, its presence is low in historical VIS published before 1950. And we conjecture that the cause is the late invention of scatterplot. Map has a long history that predates the invention of writing systems, as we know. And the invention of bar chart and line chart is commonly attributed to Playfair's book published in 1786. And by comparison, the invention of scatterplot is attributed to Herschel's paper published half a century later. And if we want to dig deeper and ask why scatterplots arrive later than other commonly used statistical charts, an interpretation by Friendly and Dennis is that line chart and bar chart were invented to show the trend of a single variable, while scatterplots was invented to examine bivariate relations, which demands more abstract reasoning and statistical thinking. Now we have seen an analysis based on our taxonomy and taxonomy labels assigned to a large collection of images. We note that the taxonomic labels can be used as a source of information for inspiring hypotheses, like scatterplots were not as popular as it is nowadays, but should not be used as direct conclusions. Our taxonomy and the labels are limited to the corpus we coded, and the machine prediction we adopted was not accurate. And future work may scale up the coded corpus and involve human quality assurance of the model predictions. Our investigation of what designs have been used in historical visualizations is preliminary in the sense that our categorization of the images is coarse-grained at the level of chart type, and the coarse-grained annotation prohibits us from detailed analysis, such as how the design of historical bar charts differ from contemporary bar charts. And then direction for future work is to use more fine-grained schemes to code the images, such as using a multifaceted taxonomy or using a grammar. Different schemes may have different trade-offs in the aspects such as efficiency of development, explanatory power, and supported usage scenarios. And additionally, one can see taxonomies, or more generally, classification schemes, as a type of human knowledge interface that mediates the interaction between human and the complex body of phenomena. And with the thinking of taxonomies as interfaces, we can retarget concepts related to user interfaces to taxonomies. And in particular, we are working on categorizing user scenarios and potential usabilities of taxonomies. And finally, to summarize, we present the protocol for developing a taxonomy based on image corpus and contribute an interactive system for this purpose. Our protocol and system are designed to be generic and reusable. Using this protocol and system, we developed a preliminary taxonomy by coding 400 historical visualization images and extended the taxonomy to the 30,000 images from OldVis Online with machine prediction. We analyzed the resulting taxonomy. And in this talk, I've skipped many details on the coding process and the result analysis, such as comparison with existing taxonomies and the debate on what is considered a visualization, which can be found in our writing. Our VisTaxa system and the related data, including the taxonomy and the taxonomic annotations, are available on GitHub. And this work is part of the OldVis project for studying historical visualizations, and the project's GitHub organization can be accessed by scanning this QR code. And thank you, that's all for my presentation.
Thank you. We have a few minutes for questions. Any questions from the room or online? Well, I'll start things off with a question of my own with this project. This is a great resource that you've put together with so many examples in it. I'm curious about the worldwide coverage of this data set. What is the scope in terms of national origin or imperial origin of some of these works, and how does that factor into the classification?
Okay, great question. Actually, I was asked this question when I presented the OldVis Online paper last year, and actually, the data set we used, the OldVis Online, was curated by scraping like digital libraries from which are mainly located in the Europe and North America, and as you would expect that the data sources are mainly biased towards like Western visualizations. And actually, next Wednesday at Kai, one of my collaborators will be presenting our follow-up work, Zhuantu set, which in this work, we create a data set from historical Chinese books. And we believe that by extending the corpus and possibly reapplying the protocol and our system, and we may possibly achieve a taxonomy that is possibly more inclusive.
Thank you. So yeah, for those of you who are going to be at Kai next week, do check out that paper. Any questions from the room? We still have some moments here. And if you have a question, please make sure that you use the microphone in your seat. I have another question about some of the beyond the national origin of some of these charts. Many of these in early instances of bar charts, scatter plots, likely came about as a result of technological change or perhaps international conflict or some point in history where there was some need for collecting new types of data. Does the taxonomy account for those variables at all?
Not really. So at the moment, our approach is that we do not consider the historical context when coding the images. And actually, you may imagine that. So in some visualization courses, we will say that, for example, there are some early examples of bar charts like Orismus illustration that shows the the velocity in some cases, people would consider like this design was came very early, like in the 12th or 13th century, and people will account for it. It is just the origin of bar chart because of its sorry, let me think. Because of its early information, but in our context, we are mainly focused on the visual appearance of the image, and because if you consider the historical context, it will introduce much like subjectivity, because when coding the images, different people will have different background on, and will have different interpretation of the images. So, but for the time being, we do not consider these contexts.
Okay, thank you again. Thank you to you, and let's give another round of applause. This paper also receives, as you may recall from last night, an honorable mention for the TBCG track. So thank you to you.
Thank you.
Okay, well, just a moment while our next speakers get set up. Our next pair of speakers will be presenting GenQA, a method for generating and validating question-answer pairs from journalistic data material. It'll be presented by Théo Lecardinel from Polytechnique Montréal and Christophe Herter from Université of Toulouse.
Hi everyone. So we are very happy to be here and to present you this work that will deal with journalism, data journalism materials that need to be presented to users, and so this is a joint project with Théo, with Thomas and myself, and from the University of Montreal and the French Civil Aviation University in Toulouse, France. And the thing that we try to do here is to present to get a new way to present information to users through questions and answers extracted from journalistic materials. But to do this, we need first to comply with journalism and their deontology. And this is very, very important because, as you know, everything that is presented that comes from any journalistic materials has to be verified, and for this question of truth and also reliability. And for this work, where we want to create a new way to consume newspaper information, both visual information and textual information, we want to use generative AI. And one of the main pitfalls about generative AI is this notion of hallucination, and which goes against this notion of deontology from the journalistic way. So if we consider this, which is the type of materials we are going to use in this research paper, we have a chart, so a timeline that shows some information regarding this annual inflation in Canada, and the corresponding article. We ask the system to generate questions and answers that the user can ask to the system. But all of these questions and answers needs to be verified by the journalist before being provided to the end users. And so this is how our questions and answers approach works, and we can see that it's another way to use it as journalistic materials, but also give access to accessibility, possibly unpaired users. So I give the floor to Théo, who will explain all the details to produce this.
Thank you. We start this project with an observation. There is no method to improve accessibility in text. Of course, there is alternative text, alt text. It's pretty easy to learn. Often it's misused already in context. What is more, the context section, the most important part for blind people, is often missing. Textualization section cannot be automatized due to current AI limit, and cannot be writing by strict rules due to the lack of uniform rules about it. So another type of method has emerged by the chart question answering. With this, user can query the system to access to a segment of this information. With this, the contextualization section is of course included. Nevertheless, this will not assure the journalistic ethic due to the lack of validation between the production of the output and the publication. That is why this can be subject to hallucination risk that we need to avoid, of course. So in this paper, we develop a third way that we use the both advantage of generative visualization description and short question answering with a generation of the set of question answer, also known as a QA, for all the data set, all the journalistic content. So we develop a new methodology named GenQA to increase its accessibility. This methodology can be divided in three parts. First will be generate all QA automatically without any human assistance. Then the journalist will validate all this QA one by one to avoid any hallucination risk. And finally, the selected couple will be published to the final user. With this, we try to avoid the hallucination risk and the spreading of fake news. So to do this, we'll be focused in this paper. We'll be focused only on the second step, the validation step, but there is many things to do and to say to the QA generation and the publication too. So to do this, we implement an interface to optimize this validation process and to make it implementable inside the professional context, inside the newsroom. For this, we designed a workflow, like you can see here in this screen, that takes in input all the QA generated by IA and as output the validated QA. In this, there is several methods and several types of methods, like clustering and visual cue. We'll explore this in the next slides. So this can be represented like this with in our interface divided in three columns. In the third column, we can see the journalistic data materials with the data visualization and the press article. We can see also a segment of this information that is highlighted in green is directly linked to the current QA that we can see in the central panel. This central panel will represent all QA textually. With this, user can read this QA and validate it or not this QA. Finally, in the third column, we have the representation of all the QA, all the generated QA. They are grouped semantically to avoid a shift between all these QA, to avoid the topic shift. More precisely, in this column, we can see another type of cluster, a syntactic cluster, that gather all couple where the question is really similar. Often only one word or two words are different, like the date, the year, or the month. There is also a contextualization section that groups all QA that are not directly linked with the data visualization or the press article. And finally, we have a bin cluster that group all QA that the answer if we don't have any information to answer to this question. So in the other part, we have a visual cue to improve this verification task. With this, journalists can focus on a specific range of the information to improve this validation. This can be also used to represent a distribution of information. With this, user can characterize some subset, like the syntactic of semantic cluster, but also all the validated QA and all the generated QA. With this, user can focus on specific QA to, for example, adopt the most uniform distribution of information to avoid any distortion of information between the original information and the validated QA. Finally, we lead a series of evaluations to evaluate this, with 10 articles validated with 3 experts in journalism. Articles provided from Radio Canada and CBC. So we highlight an interest for this different type of cluster with a decrease of validation time and also a decrease of workload thanks to our interface. For this, we compare our interface with visual cue and clustering with another interface without this tool, visual cue and clustering. So final interview also highlights the interest of journalists for the QA serendipity, thanks to the use of AI to generate this QA. Finally, we also highlight two different profiles of users, splitting according to the number of selected QA. With this, we show that there is a difference between an impact difference between these two profiles. Where an higher impact for the 10 selected QA. We explain this by the number of selected QA. Of course, for the second profile, journalists will validate all QA one by one to verify information. They didn't take in consideration the cluster. They only validate each QA one by one systematically.
Okay, thanks, Theo, for all these details regarding the way we implemented this system. And so we are really happy with this work in a sense that we were not first sure that generative AI could be reliably used with journalists, and also one of the goal of this work was to see if they could adopt such tool. So, and in fact, they do, they like it. So Theo mentioned this notion of serendipity, which is very interesting because you can imagine that the user could create all of this set of questions and answers manually, which will take a lot of time. And here in this work, we showcase that, in fact, the machine can do it, and then the user can review it. And all this paper is about the way we can review quickly and efficiently all this set of questions. And on top of that, having the AI helping us to go a little bit beyond the thing the journalist could have extracted. So it's a bit of a tedious work to validate everything, but this notion of clustering is very important because we gather all these sets of questions and answers together, and so that we can validate just few of them, so that we can validate the whole cluster. And so we also think as a future work that this work, of course, could be used to make all of this journalistic material more accessible. And we will extend this work in many directions, focusing more on maps, for instance, and really targeting embed users. So thanks a lot, and we're happy to answer any questions. Thank you.
Thank you for the presentation. Are there any questions from the room? Yes, at the back. Please use your microphone.
Hello. It's a very general question. I think it's a Gen QA. I think very general. But your paper is focused more on.
Don't hold the microphone.
Okay, good. Sorry. Focus more on the journalist request. So I'm just wondering, which part in your research is more specific for journalists? One thing. Or second question is that. Is it possible to apply your work to other types of workflow? Yeah, so this is my question. Thank you.
Yes, so in this process, the journalists only impact in the validation. So in this second part, the interest of this is to split really the automatization to the human action to avoid any interaction between these. And so for the second question, of course, another type of process can be realized with other type of clustering and also other type of visual cue. But here we try to demonstrate that it's possible to do this in our journalist content and context, and after maybe open doors for another paper.
Thank you.
Any other questions from the room? So I have a question of my own. Do you think that using a tool like this would lead to simpler or more minimal data visualizations or plainer language, clearer language in publications? And how might this interact with style guides of different journalistic outlets?
I'm not sure to understand your question. It's about the presentation of QA. So in this, we see many modalities. We explore both two of them, like present this like FAQ by listing all the QA one by one. But this can be very long. So another possibility is to create like a chatbot to answer directly to the final user. It depends of the goal of this data visualization. If it's with an educational goal or to discuss more with the final users.
Okay, let's thank our speakers again. Okay, next we have another in-person presentation, another conference track paper. It is entitled Visual Text Mining with Progressive Taxonomy Construction for Environmental Studies. It'll be presented by Samyuta Lee from the University of California at Davis.
Okay, hello everyone. My name is Sam. I'm from UC Davis, and today I'll be presenting a work that Kwang Yu and I did in collaboration with two environmental experts, Hong Chen Wei from National Taiwan University and Dr. Yuan Mei Hua from Academia Sinica. And in a nutshell, what we did is we studied their workflow and make an automated system to better support the workflow in a more efficient and effective way. So I'll start with the TLDR of our work. So like I said, we started the workflow of our domain experts and developed a system called GreenMine, which is essentially a LLM-based text mining system. And it follows this three-step prompting pipeline that we specifically designed for their purpose and our data set. The GreenMine interface supports many functionalities, such as editing the prompts, looking at the results and comparing the results of different versions of prompts, and of course, looking at the annotated data set with some highlighting and navigation support. There's also a visualization that we designed to support their communication of the insights that they mined from our system. And there's some interactive progressive disclosure support here to better support the discussion and the communication of the work. So that was the end of this TLDR. But today, I'm not going to go to too many technical details of this paper. I'm going to just focus on one concept, which is progressive taxonomy construction. And turns out this is the core of this, I think, the core of our work, and this is where all the user challenges comes from. And at the end of that talk, I'll also talk a bit more about the insights that I had from studying this progressive taxonomy construction. And spoiler alert, it's about visualization and human-AI interaction. So to understand this, let's go back to the background of our environmental study, which is using the DBSR framework. So this framework is what environmental scientists use to study and communicate complex relationships between the society and the environment. And this is a figure illustrating this framework, and it goes like this. You start with the human activities, which are the drivers that affect the ecosystem. This can be usage of water or usage of electricity. These human activities accumulate pressure on the environment, and as the pressure accumulates, state changes happen, such as climate change or sea level rise. These state changes creates impact on the human society, and in response, the human's going to make some actions, such as reducing the usage of water or turning to renewable energy. And these responses, in turn, alters the drivers and the pressure of the environment, and we repeat this process in the cycle. So now, the essence of this work is that environmental scientists use this framework in a way that is analogous to text mining. So what they'll do is they'll define a taxonomy, which describes the factors in each of the indicators of DPSIR. So for example, they can say they will only want to look at the usage of water and all the factors associated with it. And then they'll annotate the data using this taxonomy. It can be news articles, reports, social medias, or interview transcripts in our case. And as you can imagine, this is a very tedious and labor-intensive process. So naturally, we think of utilizing text mining techniques to automate. And that's where the biggest challenge comes, which is that the taxonomy is constructed progressively, which means as more insights are mined from the data, the taxonomy is enriched with more factors. So initially, they might know they want to study usage of water, but they don't know what factors are associated with it, and that has to be coming from the mining results. So in this work, we try to answer these two research questions to help them. First is how to quickly incorporate the insights back into the taxonomy, and second, how to evaluate the annotation performance given no ground truths. And to understand how we answer these questions, let's take a closer look at the process of progressive taxonomy construction. So imagine you have a taxonomy, it defines some labels, and you use this taxonomy to annotate your data. In return, you get some snippets extracted from the data and the labels associated with each of the snippet. So what we do next is you explore the annotation results, which you answer for each of the label, what are the contents of the snippets. After this exploration, you go back to enrich your taxonomy and you repeat this process. At the same time, you also evaluate the annotation performance, in which you answer this question for each of the label, does the LM understand your definition correctly? And again, after the evaluation, you'll go back and refine the taxonomy and you repeat. So you'll notice that we have an interleaved exploration and evaluation going on over here. Naturally, it becomes very beneficial and critical to support this exploration and evaluation using the same visualization at the same place. So after some study, we find that topics are really good visualization targets for exploration of the annotation results. And we use uncertainty of the model responses to evaluate the performance of the annotation of the large language models. And combining them, we designed this uncertainty chart, which I think is the most interesting part of our paper, and I'll spend more time talking about this. So in this figure, we're looking at the snippets that are annotated with the label driver. So these are all snippets with drivers. So each of the circle is a text snippet, and each colored region is a topic. So what this is showing to the user is these are all the potential drivers that the model finds from the data, and you'll find something like renewable energy, offshore tourism, or local market, stuff like that. So these are all the drivers that the model suggests to the user. At the same time, the user can evaluate the annotation performance using the uncertainties, which is encoded with the distance of a circle to the center of the chart. So it's like a polar coordinate system. The further away a circle is from the center of the chart, the more uncertain the annotation is. So you'll find that most of the circles are centered around this most inner ring, which suggests that most of the snippet annotations have relatively low uncertainty. But you'll still find some snippets, especially on the left in the pink region, that has higher uncertainty. And what it's suggesting to the user is that they should probably look at the content of those snippets and decide if these are their interest in drivers, and they'll probably want to exclude or include them by refining the definition of drivers in their prompt. Okay, so that was the visualization, and that was the core of this work, and that's how we support evaluation and exploration in the same place, and it turns out to be very useful and the core of the work. So you'll find more case study in the paper, but I don't think I have time to look at them right now. I want to move on to the broader implications, which is perhaps beyond environmental studies and looking at the concept of progressive taxonomy construction itself. And my insight, I'm studying this concept, is that when the task that you're dealing with is complex enough, the human and the AI really have to collaborate, and they both have to contribute something in the collaboration for this to work. And since the human and the AI speaks very different languages, visualizations can actually serve as a common ground to support the communication and making sure that they are on the same page. And it turns out this is called the human AI alignment in the literature. And of course, there are some more concerns and nuances in this issue of human AI alignment. But the bottom line is adding in visualizations has the potential to completely alter the dynamic between the human and the AI collaboration. And without visualizations, it's very, very hard for the human to make sense of or even evaluate the performance of the AI. And as visualization designers or the visualization researchers, we have the potential to design visualizations in a way that these issues of alignment or other ethical issues can be avoided completely. Okay, so that is the end of my talk. There are some more interesting topics that's discussed in the paper, such as using this uncertainty evaluation for other knowledge-intensive tasks, using this similar workflow for thematic analysis, and of course incorporating semantic uncertainty in our chart. And yeah, that's the end of my talk. Thank you for your attention.
Thank you, Sam. Are there any questions from the room? And please use your microphone in your seat if you have a question. So I have a question about the visual encoding, the chart that you showed, the driver chart. Maybe perhaps you can comment on, is there a meaning to the ordering of the drivers? Like they're varying arc length and not alphabetical. So I'm curious as to how to interpret the drivers in that chart.
Sorry, I'm going to show a slide that I actually prepared, but I didn't show it. Okay, so this is actually the encodings behind this chart. I didn't really have time to go into this, and I borrowed the design-specific transformations that Remco talked about a few days ago to illustrate this. So for your question, the order of the topics is just decided by the semantic of the topic itself. So closer topics will be closer together, like dimension like what we did in dimensional reduction, and but it's not entirely mathematical or truthful, because what we find in this particular case is that the user doesn't really care about the exact accurate distances in the semantic embeddings. What they care about is probably the relative distances between the topics, and that's more of a fuzzy coding, fuzzy distances. So we actually did this space distribution and some force layout to avoid to avoid the visual cluttering, but it's at the sacrifice of mathematical truthfulness.
Thank you, and wow, thanks for the supplemental slide there. Question.
Quick follow-up. So the rings are still distances though, right? Or what do the rings do?
The rings are the uncertainties of each of the snippet.
The what?
The uncertainty of the model's response. So so what you're looking at is, for example, all of the nodes here are annotated with driver. That's a labeling, that's an annotation, and that annotation is generated by large language models. So we measure the uncertainty of the model's response, and we encode it using the distance from here to the center, like a polar coordinate system. And the angle is the semantic differences between the topics and the nodes.
Let's thank the speaker again. Thank you. Okay, we have another in-person conference paper talk. This will be delivered by Ines Kanarajan from the University of Stuttgart. The paper is called The Joy of Co-Painting, Creative Human-AI Collaboration for Traceable Image Generation Workflows.
Hello, thank you for the kind introduction. So my name is Ines Kanarajan. I'm with the Visualization Institute of the University of Stuttgart in the group of Stefan Koch. And I'm happy to present you our work, The Joy of Co-Painting, Creative Human-AI Collaboration for Traceable Image Generation Workflows. As you might already know, image generation models are very popular, they're very powerful, and you can use them for generating pretty much anything you can imagine, by using a natural language description of what you want, which you call a prompt. And if you've used one of these models, you might have also encountered that in some instances, what you prompt is not necessarily what you get. So what I mean is that for complex creative tasks, for example, involving abstract motives or something like very specific targeted concepts or compositions, conveying that in a prompt can be pretty difficult. To provide an example, this is one of many attempts of using ChatGPT to create an image of the famous painter Bob Ross in a mysterious forest, assessing a self-portrait of himself, drawing himself. So for one, we have this sort of recursive self motive, and on the other hand, we have the mysterious forest. And as you can see, the image is pretty good already, but it's not quite what I envisioned, because I would have had like the forest to be more present. And I could try to change that. I could add maybe some keywords to the prompt and I rerun the generation, and maybe I get what I want, but maybe I don't. In the latter case, I can again adapt the prompt and try again. And I get sort of into this trial and error loop where I try again until I sort of approximate what I want. Instead, I used our approach where we combine a little bit of provenance visualization with parameter sampling, image editing for targeted image creation. But to go a few steps back first, key challenge we wanted to address is how can we effectively realize our creative intents in targeted image creation? Of course, we are not the first ones to ask this question. And if you look at existing literature, one of the primary focuses, of course, is prompting. So a lot of works research how we can guide users in the prompt refinement process. And for example, by visually representing how changes in the prompt affect the results, and in that way help them in adapting the prompts. Complementary to that, we also have a lot of works that now do some form of visual recording of the generation process, since, as I've hinted before, there's always lots of exploration, experimentation involved. In the end, current works are still very prompt-centric, and the human involvement is often limited to some form of prompting. And we realized that this is maybe not the most effective way for targeted creation, and that there are some more other tools we can utilize for this. This is why we propose a new image generation workflow that combines a graph-based overview for better traceability of the entire generation process, for more transparency, and for better reproducibility. As a different option for more model control, we propose visual parameter sampling. So there are some hyperparameters involved when using image generation models, and I would like to go more into detail, but unfortunately due to time constraints I can't. But let me tell you that these hyperparameters can significantly change the outcome of the result. And we visualize how changes in the parameters affect the image results. And we integrate all of this into existing image editing workflows to encourage users to utilize manual refinement of the images without interrupting them in the generation workflow. For the graph-based overview, we introduce something called a provenance graph, which is a node-link diagram inspired representation of the entire generation workflow, which also embeds the generation. So we integrate a image editing model, in this case the open source model Stable Diffusion, which users can utilize to generate the images. And generated images are shown as so-called image nodes, and consecutive generation results are always connected by an edge. The edges also show something called a parameter node. This is a visual representation of all the parameters and the settings necessary to reproduce the result. The provenance graph also integrates the visual parameter sampling. So the idea is that users can not only set the specific values for the exposed parameters, they can also define entire ranges for the parameters. Then we generate an image for each specific parameter constellation, and the resulting images we then visualize as projections. To emphasize the similarity between the images, and we do this by vectorizing images and then dimensionality reducing them using UMAP. Lastly, we connect our provenance graph to an existing image editing tool. In this case, we use the open source tool Krita. And the idea is that users at any point during the generation process can take any image from the provenance graph and one click, import it into the image editing tool, their manual refinement, and then layer-wise export the intermediate results again into the provenance graph and seamlessly continue with the generation. To evaluate our approach, we conducted a user experiment. We invited 9 participants with varying expertise in image editing and image generation. And we asked them to perform 2 art creation focused tasks. And to give you a rough rundown of what the tasks are. First one was more targeted. So we gave them a landscape image and asked them to remove any distraction features. And we defined distraction features as anything related to humans, tourists, or man-made objects like trees and so. The second task was more open-ended and creative and involved utilizing the result from the first image and making it into a fantasy image by introducing any fantastical elements the participants could think of. This here is one of the results for the second task of one of the participants and shows a pretty complex provenance graph where the participant utilized basically all the tools we provided. We paid special attention to the strategies and the workflows the participants employed, and we found that the experience heavily shapes the workflows, and that depending on the experience, all participants had a pretty unique way of achieving the results, and this also reflected always in the provenance graph. So for less experienced participants in image editing, image generation, we saw that they basically used our tool as a learning tool to learn on the fly how the generation works, and also utilize a little bit of parameter sampling to augment their results. And the more experienced the users were in image editing and image generation, the more they utilized the visual parameter sampling, especially for experimentation, for example, in the ideation stage. And they heavily used manual refinement, basically at any point during the generation process for very targeted changes in images. To conclude my talk, we designed a provenance graph as an overview for better traceability of a generation process and to encourage users to redo and undo steps as they needed it. Visual parameter sampling is a powerful tool both for additional model control but also for experimentation. Integrating image editing directly into the generation workflow encourages users to make use of manual refinement as a valid alternative to repetitive prompt refinement, prompting for targeted changes. Of course, there's always room for improvement, so some things to consider for future work. One is the scalability of the provenance graph. So this one can get pretty large and handy for pretty complex workflows. There's also room for improvement when it comes to the responsiveness when using parameter sampling. So as you might imagine, if you take really large parameter ranges, the number of images you generate can blow up a little bit. That takes time. And lastly, as I said, we are less prompt-centric in our approach. So we do support basic prompting, but of course you could always implement maybe a state-of-the-art prompt improvement method and see how that further influences the workflows. All in all, we presented an effective new approach to human-AI collaborative image creation, which supports both novice users and expert users, but reaches its full potential with the experts. I thank you very much for your attention, and I'm open for any questions you have.
We have a couple of minutes for questions. Questions in the room? Yes.
Is your tool available online?
Kinda. Integrating, thank you for the question, of course. Integrating this image model online was a bit of a hassle. It will be available online at some time.
Okay, that's too bad. Because to be honest, if you get that kind of answer at the end of a conference talk, it means never. But it would be lovely to be able to play with this.
I will make sure it goes online.
Excellent.
I promise that.
Yes.
So thanks for the presentation. Very, very interesting. So I would love to play with that, but I'm going to chat a little bit with you. But so just to be sure, all your system is agnostic to any diffusion model, or is that really specific to any image generation model?
No, it's agnostic. You can use pretty much any model. We used open source models.
Okay, and so and next question would be, what, because you have many users who use your system, did you get any feedback where they struggle to get a specific modification of the image? So I'm really interested into that. They really want to have this specific item, and they're going back and forth between the generation, and it's not exactly what they want. And so, do you have anything to report on that? What is the most difficult thing users manage possibly to solve with your system?
Yep, pretty much that. So this was just a very rough summary of what they did. There's of course, a larger summary of that in the paper, but this very targeted changes, that's something that's much easier possible for our tool, especially in combination with parameter sampling, because there's one parameter that can control how much your image changes in comparison to the image before, and that combination really helped to do that.
Okay, I will discuss further with that.
Yes.
Thanks a lot.
Okay, that's all the time we have for questions. So thank you very much, Ina. Let's get another round of applause. Okay, the next presentation we have is actually the winner of the best paper of the conference track at the conference, which is More Than Beautiful, Exploring Design Features, Practical Perspectives, and Implications of Artistic Data Visualization. It'll be presented remotely by Xingyu Lan from Fudan University. Can you hear us?
Oh, yes. Hello,
Okay.
hello. Can you hear me?
Yes.
Oh, okay. Thank you. Hi, everyone. Today I'm going to present our paper, More Than Beautiful, Exploring Design Features, Practical Perspectives, and Implications of Artistic Data Visualization. So this paper was co-authored by Xingyu Lan and Yifan Wang from Fudan University, Liu Yupeng from Harbin Institute of Technology, and Xiaofan Ma from Sun Yat-sen University. Artistic data visualization refers to visualizations created by artists with the intent of making art. It has gained widespread attention in recent years. As the BBC has reported, artists are now making waves with big data. Some data-driven artworks have been exhibited in significant events and even sold for millions at auction. However, although artistic data visualization is getting lots of attention in society and the art industry, it's still underexploited in academia. Firstly, compared to its flourish in industry, research focused on artistic data visualization remain relatively scarce. Secondly, some studies have explored isentics. However, most of these studies have simplified isentics to hedonic features like beauty, without delving into the nuanced connotations of isentics. Lastly, the value of artistic data visualization is still in controversy. We need more insights from artists and practitioners. So to address these gaps, we took an initial step toward understanding artistic data visualization. To begin with, we present case analysis on 3 representative artworks, including Dan Sadin's VR art, Kat McLean's smell maps that visualize people's subjective feelings about smells in cities, as well as Rafik Anado's machine hallucination, a series of artworks that incorporate machine learning in the creative process. Derive a more systematic understanding of such art practice. Next, we collect a corpus containing 220 data artworks and conducted a more in-depth analysis of their design. To be brief, we mainly coded 3 dimensions: design paradigms, design intents, and design techniques. Our findings are as follows. First, design paradigm. These are the high-level creative lenses that guide the whole approach. Across the corpus, we identified 37 explicit mentions of such paradigms, we found that artistic data visualization can be fundamentally shaped by high-level design paradigms. Second, we analyzed the intent behind the work. We found 15 categories in total, 10 that aligned with existing effective visualization work, and 5 that are new, including represent, criticize, equip, analyze, and witness. For example, architecture represents the experience of listening to music by transforming the artist's subtle emotions into animated metaphorical shapes. The Sky is Falling shows the number of civilians killed by US drone strikes. The artist performs in the desert from dawn to dusk, commemorating each civilian with the data physicalization. Viewers witness the ceremony through live streams. Compared to earlier work, these intents are more varied, and their distribution is quite different. This suggests a broader and more expressive intent landscape in artistic data visualization. In terms of low-level design techniques, we identified 32 distinct techniques, grouped into 4 categories: sensation, narrative, interaction, and physicality. Due to time constraints, we are not going to delve into these techniques one by one. But in a nutshell, we observe that, unlike traditional charts, many of these artworks take the form of installations of physical artifacts. We also compared the design techniques of the artistic data visualization with those identified in effective visualization design, finding that interactive technologies in artistic data visualization are more prominent. These are manifested through various body, face, and gesture-based interactions. Meanwhile, the use of physical materials is more diverse and pronounced, incorporating a wide range of materials to encode data, such as metals, furs, food, and even microorganisms. So far, we have shown how artistic data visualization can be designed. But what about artists themselves? What motivates them? How do they think about their own work? To find out, we conducted interviews with 12 data artists. The interviews yield rich findings. For example, we identified 4 types of motivation. Some artists are value-driven, guided by high-level philosophies, theories, or thoughts. Others are interest-driven, starting from a personal fascination or past experience. Then there is reality-driven, where real-world events put them to respond, such as environmental issues or cultural loss. And some are client-driven, creating works based on business needs. In terms of how artists understand and describe artistic data visualization, we found that the words like emotion, expression, and narrative came up frequently. In general, artists place a strong emphasis on human agency and the expression and concepts. Unlike scientific visualization, which values objectivity and precision, artists embrace subjectivity, ambiguity, and personal interpretation. Meanwhile, we also collected a series of responses from artists regarding critics or doubts and the challenges and expectations they perceive. To summarize, we found that artistic data visualization is deeply rooted in art discourse, with its aesthetic pursuits particularly contextualized within contemporary art philosophies and values. So the next question is, how can data art bring value to visualization field? And where can artists and scientists inspire each other? Based on our findings, we propose several lessons for future work, which we marked from L1 to L7. For example, we argue that there is a need to broaden our understanding of aesthetics. Although previous research often simplifies aesthetics to hedonic features, artistic data visualization shows that aesthetics is not just about beauty. It can be critical, intentionally messy, or even ugly. As shown by the visualization on the right, some people may find it terrifying, but this is intentionally done by the artist to embrace anti-beauty and depict the world seen through the eyes of machines, thus challenging human-centric views. L4 is about learning from artistic styles. For example, some prior work has already adapted styles from painting or motion design into data visualization, like applying the style of traditional Chinese painting to maps, or extracting color palettes from impressionist paintings and applying them to scientific visualizations. This approach opens up new expressive potential for visualization design. L5
2 minutes remaining.
encourage us to explore alternative sensory channels represented by rich data visualization sonification artworks observed in our corpus. In terms of application research, for example, L6 calls for building tools for artists or users who want to design like artists. For instance, through creativity support systems, we can help users sketch their ideas, easily incorporate art resources and styles, or generate personalized visualization design. So to conclude, the work contributes three things. The first, empirical understanding about the design paradigms, intents, and existing techniques of artistic data visualization by analyzing a corpus of artworks. Second, first-hand insights practitioners and provide valuable perspective and foster community dialogue. Third, guidance for future work to explore new possibilities and advancements inspired by the dialogue between art and science. So that's all. For more detailed information, please refer to our paper and website. So now is the Q&A section, so feel free to ask me any questions. And I see there is a question online.
Yes, I'll read it out loud because people in the room haven't seen it. There is a question online from Freya asking, I wonder what difficulties might visualization artists and professional researchers / scientists encounter when collaborating across disciplines, and how do you think these challenges can be addressed?
Okay, good question. Actually, we have mentioned it in the paper, but not in this presentation. So we can come back to the perspective from data artists. For this insufficiency of the collaboration and understanding, so many artists that we interviewed hope for scientists to join in and enhance professional knowledge of data and to collaborate with teams specialized in data processing. Like if you want to get some generative art, you best have experts in algorithms. I remember that one artist we spoke to pointed out that people doing artistic data visualization come from really different backgrounds. Some started in tech and is interested in art, and another group that they are the artists from the start. I still remember one of the artists we interviewed said, he said that it often feels we are not speaking the same language. So the gap in training and mindset, it can make the real collaboration very tricky. How to resolve this problem? I think first of all artists and scientists should actively recruit disciplinary collaborators. And another solution is that we can back to the lessons we show. We can developing tools designed for both artists and researchers. Let me back to this pages. So in our L3 lessons, we say that we can have some incorporating disciplinary methods. In our paper, we show that regular workshops, brainstorm sessions, and hackathons can foster mutual understanding. So I think this allows both sides to learn from each other's strengths. Artistic creativity and scientists' technical expertise.
Ifan?
Hi.
Unfortunately, we're running out of time. We're running short. We'll have to move to the next presentation. But
Okay.
thank you for answering the question, and thank you for the online question.
Okay,
from Freya.
thank you.
Before we move to the next presenter, if the presenter of the last note in this session, the paper Matic, is here, please come and see the technician to set up in advance of your slides. But for the meantime, we'll now move on to our first of 3 notes. So our next presenter is Soon-Gon Kim from KAIST, who will be presenting Chart to Experience, Benchmarking Multimodal LLMs for Predicting Experiential Impact of Charts.
Okay, hello everyone, good morning. I'm Sun-Kyung Kim, and I'm going to present our short paper named Chart to Experience Benchmark Paper with the Multimodal LLMs for Predicting Experiential Impact of Charts. So let's start with the simple question. So which chart would be more memorable to the ordinary audience, the left or the right? Actually, we conducted a crossword study, and the participants answered that the right chart is more memorable. And what about the other aspects? Their scores were similar in terms of interest, trustworthiness, empathy. But they also answered that the right chart was more aesthetically pleasing, intuitive, and comfort. As you can see, the factors here are commonly considered while designing the data visualization, and it would be helpful for designers to predict such impact to the ordinary audience. So our research question was like, can multimodal LLM accurately predict experiential impacts of charts? Prior research has identified the various experiential factors. For our study, we selected a few of them. While selecting the factors, we tried reducing the redundancy, for example, like merging similar factors like engagement, joyfulness, amusement into interest, a single one. And secondly, we selected the factors which are testable without contextual information, such as the opinion and demographic of the readers. As a result, we selected these 7 factors listed in the below. In order to conduct a user study, we first selected 3 widely used data subjects, which all offer various chart designs publicly available. Then we collected 12 charts for each subject via Google image search and came up with a 36 charts purpose. For the study, we gave a chart image and the questions for the factors. For each question, we asked how much do participants agree with the question in a 7-level Likert scale. And also, we received the reason behind the scores. Participants answered to these with all 7 factors and repeated with 6 charts sharing the same subject. So this is an example image of a ground truth data. All the data can be accessible through our website with a simple interactive chart for exploration. Okay, since we have a ground truth data right now, we are now prepared for testing the capability of the MLMs. For this, we use 2 tasks. First, we made an MLM to generate absolute scores like human did. And second, we directly give a pair of charts and let MLM to compare them. Let's start with the first one. Just like we had collected scores from different 36 participants for each chart, we repeatedly called the MLM evaluation for 36 times. In order to differentiate the MLM scores, we generated artificial persona and used them for prompt engineering. You can see the example of the artificial persona in the text box. This table shows the mean and standard deviations obtained from human and 3 different MLMs, which are Claude, GPT, and Llama. Mean values vary across the models. And there is no consistent direction of this variance since Llama is consistently giving lower, while the other 2 is giving higher scores than human. Also, all models show relatively small standard deviation compared to human, which means that the MLMs are not sensitive as much as human to varying chart designs. Based on the patterns that we observed, can we say that the models are inaccurate? What if the charts were consistently scored in a rank order, like this? We had to check rank correlation too, since these differences can be normalized or can be fixed with prompt engineering strategies like a few-shot prompt, providing sample scores. Thus, we added a non-parametric correlation measure, which is a Kendall style. This table shows the Kendall style correlation coefficients and corresponding p-values. While many scores made by MLMs are positively correlated to humans, half of them are insignificant, and their size were not that large. Then what about the performance of pairwise comparison? We made MLMs to look at a pair of charts, then predict which chart would be received higher score from ordinary people regarding the question. And for the MLM prediction, we mark it as correct if the MLM successfully finds the chart with higher human score. So in this case, MLM was correct. When considering all the chart pairs, GPT and Claude achieved about 70% of accuracy, while Llama showed around 50%, which is similar to coin flip. However, if we assume this comparison task is similar to determining whether the difference between the ground truth scores of 2 charts is distinguishable, we need to look deeper with these differences. For example, a difference between 2 charts would be really subtle in terms of human scores, like if it's in a range of a small range, like for example 0 to 0.2. On the other hand, there might be pairs where the differences are larger, so that they seem easier to determine the winner. Based on this idea, we analyzed whether the performance of MLM depends on these human score gaps. So this is the result of the pairwise comparison. The bottom 7 charts are for 7 vectors, and the top gray one is a aggregated one. Y value is accuracy, while the X value is a bidding category. So bidding category, for example, with the delta value within 0 and 0.2, we sum up the cases here. And for the 0.4 to 0.6, we aggregated the cases, accuracies are here. One of the most salient pattern here is that MLM tends to be more accurate when the pair with a higher human score gap is given. One interesting point is that despite this rising trend, there are notable falls when looking at interest and aesthetic pleasure. We investigated these incorrectly predicted cases and found that particular charts and their visual characteristics were evaluated as highly impactful by MLMs. For example, those wrong cases almost contain one of these 2 charts. For this clover heat map, MLM tends to say that vivid color scheme is really interesting and aesthetically pleasing, while human mentioned that difficulty in reading and unpleasing color encoding. So, conclusion, takeaways. First, absolute score prediction without prompt engineering or normalization seems unreliable. Second, MLM's accuracy of pairwise comparison increases as human score gap between the charts increases. And last, cases where comparison accuracy remains low despite a large human score gap can reveal the differences in perspective between the human and the model. Thank you for listening.
We have a couple minutes for questions in the room. Any questions? speaker? I'll start things off with a question of my own. I'm curious about how, if the context in which these charts appear would impact the performance of the MLLM in predicting its experience, such as if it's in an online article, or if it's encountered on its own, or if it's in an infographic, or some other context, if it's in a television ad or something like that. What does the medium? What do you expect the medium to have a impact on its performance?
That's a really good question, and thank you. We all know that the data visualization cannot solely stand, and we while constructing the 36 charts corpus, we had a lot of idea about should we include a texture information like a article text, the article title, or the caption, something. But we decided just to focus on the visual attributes, the visual interpretation of the charts only, and see the capability of interpreting that those visual attributes of the MLM. So we just included with the textual information, title, subtitle, or the source, and those kind of things. And context, solely standing chart. Okay. Thank you.
We have a question in the room.
So the three cases that you picked to do the experiment, global warming, house prices, and COVID, I think, at least in the US, they are highly controversial and political issues. So I wonder if you have found any biases, like political biases in the LM's preferences on your result.
Well, actually, I didn't analyze the biases of MLMs based on the provided reasons behind the MLM scores. However, with the subjects, we try to be like neutral, like excluding the politics. You know that there are a lot of charts about the U.S. elections or the sports games. We may have a lot of interest or some emotional feelings about them. Maybe unlearning or just excluding the responses manually to solve those biases. I'm not sure. Yeah.
Okay. Well, thank you, speaker. Again, we'll also congratulate you for the best note for PacificVis 2025. Thank you again to our speaker. Our next note presentation will be entitled Automated Pipeline for Detecting and Analyzing Misleading Visual Elements. And our speaker is Min-Young Kim from Seoul National University.
Okay, thank you for the introduction. I'm Min-Young Kim from Seoul National University, and today I'm presenting our recent work titled Automated Pipeline for Detecting and Analyzing Misleading Visual Elements, which was done with 6 wonderful collaborators. And yes, our work is about misleading visualizations. And I think all of you might know that visualizations are really powerful tools for communication. But however, visualizations are not flawless, and I will give you some examples. Here's one example. Can you spot anything strange in this visualization? Or since there's no one answering, I can give you a hint. Now, can you find anything strange? Yes, the x-axis is distorted. And a correct visualization might look like this on the right side. And there is a really big difference on how the visualization looks. Here's another example. Can you spot anything strange in this visualization? And again, I can give you some hints. obviously the numbers and the lengths actually don't match in the visualization. And a more proper depiction would look like this on the right side. So here we can see that visualizations actually can be misleading. And this causes problems to users when they encounter these visualizations in the wild. So the core issue is twofold. Users must first identify misleading visualizations, and if they are, then they should subsequently understand why these visualizations are misleading. And there are actually visualization guidelines previously developed. For example, this work in 2021 provides linting for visualization designers using VegaLite. However, visualization guidelines have notable limitations. They're often difficult to consume, they leave interpretation solely to the reader, or can apply to only limited contexts and issues. This is because guidelines are for designers, not readers. For example, a guideline receiving input as VegaLite specs, like you saw before, might help designers produce visualizations without error. However, readers rarely have access to these specifications of the image, and such systems cannot help the reader. Thus, for a reader to effectively find out whether a visualization they are seeing is misleading or not, we need to know three things. One, whether the visualization is misleading. Second, what elements in the visualizations are misleading. And last, why they are misleading. And to provide answers to these three questions, we draw from two models. And the first is large language models. Recently, research have found that large language models, such as GPT-4 models, are very effective in identifying misleading visualizations, even when using naive zero-shot prompts. This is an example. As you can see, there are various kinds of misleading properties of visualizations, including reasoning and design misleaders. And all of these kinds of misleading features can be identified with large language models. And the second model is image segmentation models, where we can apply such models to distinguish single elements inside visualizations without any other information than the bitmap image itself. So this is, I think you might be familiar with the image you just saw about 2 minutes ago. And as you can see, the segmentation results can distinguish between the different bars and labels in the visualization. So, utilizing these two models, we achieve automated identification of misleading elements in visualizations, and more importantly, generate specific explanations for their misleading nature. So here is our pipeline overview. Our pipeline is constructed of 5 steps. The first one is segmentation of the original visualization image. And then we extract the labels from the segmented objects. And also, from the original image, we conduct misleading issue detection. And then we decide the relations between the found issues and the labels. And last, we validate the issues and labels and then annotate them onto the original image. And all of these are performed with GPT-4o model. And this is the output of our pipeline model. So as you can see in the image, as the user hovers on the specific label, you can see the object corresponding to the label on the left side. And also, for each issue, there are explanations of the issue provided to the user. And also, the user can see which specific labels are related to the issue. So to find how effective our pipeline was, we designed this user study of providing 3 types of results. The first was a simple text results from prompting traditional design guidelines, and then results from our pipeline without annotations, and results from our pipeline with annotations. And from the results, we can see that users found more true issues and less false issues using our pipeline. This means that element-wise detection is actually effective for the users. And also, when we asked the users to fix the found issues, users made more good fixes and less bad fixes or unresolved issues provided with our annotated pipeline. And the users also reported that this was thanks to the provided annotations and them enhancing the explainability of the issues. And also, we found that there is a trade-off between accuracy and quantity. But with more thorough guidelines, users tended to get overwhelmed by the vast amount of information and find more false or irrelevant issues. And they also generated more bad or incomplete fixes. Here we see that while leveraging LLMs can make more comprehensive feedback possible, how the feedback is filtered and conveyed to the user must also be considered. And also, our qualitative results provide takeaways on how users interact with misleading visualizations. Mainly, we found that users actually utilize the system when finding issues, but they mainly use their prior knowledge when they fix the issues. Also, users did ignore some suggestions if they thought those were inaccurate. And this behavior was stronger if the user was more confident with visualizations. And users who were not familiar with visualizations tended to rely on the system and accept all suggestions whether or not those were accurate. So in this work, we confirmed that visual annotation significantly reduced misinterpretation. However, questions remain about optimal annotation methods to maximize effectiveness. For example, some participants in our study suggested that using bounding boxes is less effective than highlighting effects. So one route of further research may clarify such problems, and they might aid a more effective tool for preventing users from misinterpreting visualizations. And another direction of future work is enhancing the performance of these systems. The current work was done with GPT-4o model, and even during the short period between the study and the presentation now, many more developed models have been published, some including automatic image segmentation. So this further highlights the importance of our study. We verified that such image segmentation, combined with the power of large language models, can provide users with more accurate and effective feedbacks on misleading visualizations. Thank you very much for your attention, and I'm now very happy to take any questions you might have.
Thank you. We have a couple minutes for questions in the room. I have a question to get started. Can you comment on the visualization literacy of your users? Did you administer a test first to calibrate their prior visualization knowledge or their experience with different chart types before you assessed them?
Yes, we had a pre-study interview. So the users answered actually how familiar they were with visualizations in total, and then line charts and pie charts and scatter plots. In a 5-point Likert scale. And actually in our paper, we have sections where we explain how the users kind of acted differently according to how they were familiar. And as I mentioned, they actually users more familiar to visualizations tended to kind of be more skeptical to the suggestions from the system. And yeah, so.
Thank you. We have time for another question from the room, if there's one. So if not, I have another question. You mentioned the opportunity to fix the chart afterward, but you also mentioned at the beginning of the talk that this was supposed to be reader-centric rather than author or developer-centric. So perhaps I missed that, but can you clarify, what do you mean by fixing the visualization? Is this just a verbal response that was given to you, or were they actually expected to do some design work themselves?
So during the study, we asked the users to fix by actually, we gave the visualizations to the users by a tablet, and then they just drew simple ideas on how the misleading issues could be resolved. So that was to check if the users were actually understanding where the issue comes from.
Thank you. All right, if there's no other questions, we'll move on to our final note presentation. So let's give another round of applause to our speaker. Okay, so our final technical presentation of PacificVis 2025 in the end of this session will be a note called MATIC, Multilingual Accurate Textual Image Customization via Joint Generative Artificial Intelligence. The general chair reminded me that this paper also won an honorable mention for best note as well. So let's give a round of applause for that as well. And the speaker is Xiaoxin Wu from National Taiwan Normal University.
Introduction. I'm Xiaoxin Wu from National Taiwan Normal University. And today I want to share my work, MATIC, Multilingual Accurate Textual Image Customization via Joint Generative Artificial Intelligence. So today we will go through introduction, system implementation, result on textual image, and in the end is conclusion and future work. So why we wanna to work on this project? Because nowadays we already have a lot of diffusion model. They can generate very interesting or very beautiful images, but it cannot provide a very informative illustrated image. So we can like use it as an educational content, or like when we want to have a chart, we cannot just generate by our diffusion model nowadays. So the challenge here is if we want to generate a textual image, the texture itself requires high detail complexity and high consistent requirement, meaning that if the text like break at some point, then we won't consider it is a correct later. So we will face these four common issues below. The first one is lack of multilingual support, because most of the diffusion model is trained on the English content, and English content is like more simple. It's only 26 letters, but in like Mandarin is tons of words. So it will lack of multilingual support. But even in English, it will still facing incorrect spelling, letter confusion, and text blur. So here we propose a system called MATIC, Multilingual Accurate Textual Image Customization. We separate the difficult part with the train of thought concept, because if we want to do a text one at a time, it is very difficult. So we just break it down into a very manageable part. In our work, we only use diffusion model to generate the image without any text. And then we use multimodal large language model to do position detection, style modification for the word. And we will generate the parameter. In the end, we will use this text parameter and then fuse the text back to our image to get our final textual image. So here we can see our system implementation. We have four major modules, as we can see the green one. We will have content design, potential text cleaning, fusion, and fusion evaluator. So let's break it down and start from the first one. It's content design module. So in content design module, our first goal is to separate the generation of image and text. So we can see there have two components, text information generator and DALL-E prompt generator. In text information generator, we will consider about the language and the content in the textual image that we want to present. And also the most important one is the text information. Because in an image, we will have like a lot of text maybe in different blocks. For example, if we want to generate a movie poster, it will have the title and also the director's name and the director's title. We want to make sure like our next module can receive all this information so it can place the text at the correct section. Also, because we directly use DALL-E as our diffusion model, and DALL-E doesn't understand negative prompt. So if we told it that we don't want any text in it, it cannot understand. So we will refresh our prompt for DALL-E. For example, if we want to generate a Mother's Day card, we cannot just tell it, oh, I want a Mother's Day card, but no text in it. It still will generate. So we will refresh it as like, we want a card, but with an empty card with like mother and children icon in it. So after our DALL-E receives the prompt, we will generate an image. And we need to make sure that the image itself doesn't have any text in it. So we will go through a potential text cleaning module. It is also in use multimodal large language model. So at first, we will go to text scanner. If there is any text in it, then we will go to text implanter and automatically identify the text itself and then remove it. If it's not, we will just directly send to next module. So our next module, Fusion, will receive text-free image and desired text information. At first, we will detect the position for the text, which part is the best. It will based on the language, because most of the language is left to right, but in Arabic is right to left. So here we will also consider about the language. And also the image itself, like where we will do edge detection to see where the edge is less, so maybe we can put the text here. After we have the parameter of the text position, we will send to Glyph Designer, and it will choose the font from our font database, also recommend the suitable font size, color, and shadowing. Then we will send all the parameter to our mapper so it can fuse the text and image together. After we receive our textual image, we will go to Fusion Evaluator. Our system at first will to evaluate if the text is all correct and within the image boundary. If it does, then we will send to our user. And if it does not, we will send back to our Fusion. And now, because it is a multimodal large language model, our user, when they want to modify the image, we can just directly input the natural language request. Like they don't need to use any code or any specific technique. And our system just can modify it we can see it on our result later. So the first one is the result on textual image. We can see this without the lens contrast, so we didn't care how many words is in the image. The first one is Stable Diffusion and DALL-E. These are the two common diffusion model that doesn't have any interest in textual image. But for text diffuser, 2diff text, and custom text, they are more want to modify the text in the image. But all these 5 work is all based on diffusion model only. So its limitation in the textual image generation is still very difficult. But in our Matic project, because we separate the diffusion, the text from the diffusion part, so we can have a very steady and high quality in a different language. And even with the length construct here, we can see we have the different numbers of word and the accuracy. And here we choose to compare with the Text Diffuser 2 and DALL-E because they have the open source that we can check. So the first one, we can see the accuracy is calculated by how many image I need to create to have 10 correct image. So here we can see even with the length constructs, we still can maintain a very high quality. The next one is the visual result. We compare with the Text Diffuser 2, and it's for an educational concept. So the prompt here is in math class in English or biology class in Russian. And we can see because we have the content design module, so our image can more directly with our prompt, but but if in Text Diffuser 2, even the English is correct, but the image itself and with the prompt is a little bit different. And for the user revision, we can see the reference image up there is provided by our system. And our user can say, oh, I want the title in French or move the title around the hand. They can just type in this comment, then we will just directly change for it. So our conclusion and future work is our Matic can provide a very stable and high text accuracy among different language and text lengths. And because of the chain of thought concept, each module can localize optimization. So it can address the diversity cultural needs. And in the future work, we may update the font database with more generative fonts or develop our user interface. That's all. Thank you.
Thank you. That's right on time. Are there any questions for our speaker from the room? Yes.
Thank you for a great presentation. I'm so curious about, because here we are in the visualizing conference, so I'm curious about how this, your wonderful, the system can be applied to enhance the data visualization and visual analytics practice.
I think because when we want to provide educational content, we can use our assistant to directly generate from we can change the textbook to more visualization content. So it's more helpful for children to learn.
Oh, thank you for the answer.
Yes, from the back.
So the image you provide or have 2D kind of text. If you want the large language model to generate, say, a 3D street scene with shop signs, those texts will be as perspectives, right? Would the method you propose work in that scenario?
This in our future work, because like nowadays only for the flat one, but in the glyph designer-led component, maybe we can reshape the text to fix in the image more.
Yes.
Have you run into any limitations around high density text, and what do you think could be done, if so, to improve that? High density, like a lot of text in a small area. Did you have any limitation on the generation, or?
You mean like how long? Contracts of the.
When you get into like a paragraph or something, did you have any issues with generation and so? Because all the examples I saw just 1 or 2 words on the screen.
It's more like it will be constrained by the image size itself, but even in the length, it would be not that hard to generate.
I think we are just about time for questions. So let's thank our speaker again, and congratulations on your honorable mention as well. I believe so. We're a few minutes behind. We have our final keynote session at beginning at 11. I think that's still the plan. I have not heard otherwise. So we have time now for coffee. So thank you.